of whiteboard.
Okay, perfect. Yeah, I just want to clarify something that I wrote last time, and Ricard asked why the K mu nu, that is the extrinsic curvature on sigma, is symmetric. So I just want to briefly do that, just to make it clear. So I wrote the K mu nu on sigma is Q mu rho Q nu sigma and sigma. You remember that this Q is the metric on sigma here, and this nabla here is the Levi-Civita connection G compatible. So we have that, I mean, G compatible and torsion free. So this nabla here is with G, not with Q. And this N sigma is the normal vector on surface. So for example, we have something like this, and this is, say, just a second. Okay. This is all of M, the space-time. This is sigma here. So for example, let's take a point here, X, and this is the normal vector N mu. Yeah, so yeah, I just want to remind that this nabla here is torsion free because it's now important. So since we know that we foliated the space-time to these sheets, and this sigma here correspond only to one sheet, then this sigma is a level set, say at a specific time t, fixed t parameter, is a level set defined by some function f. That is, we can write this as f of x, where the x mu are the coordinates for this m here, and this is constant to some t, so it's constant in time, say. This can also be proven by inverse function theorem, where we can define, you know, at least a neighborhood of a point x here, where we can write such a neighborhood as a function of the coordinates, and that's a constant of t. So in this case, we know that at least the gradient mu f is orthogonal to the level set of such a function, you know. So we can write the n mu, so the normal vector free some other function f as a, you know, as a coefficient, say coefficient, but it's a function, of course, depending on the space-time coordinates. So in total, we can write this normal vector in this way. And now this is important because when we say we want to write the antisymmetric part of this, so for example, we want to write something like this. So if the antisymmetric part is vanishing, then it's of course symmetric. And so we can write this as the antisymmetrization. Of course, the antisymmetrization on Q nu correspond also to the rho sigma, of course. And now we write this as you know, just using this formula here. And so we apply this nabla on the f here, and also on the other part on the...
Yeah, you forgot the capital F.
Oh, sorry, yes. Yes, sorry. Plus rho f sigma f this way. Okay. So yeah, just some mess. And so now from this term here, we know that this is vanishing because nabla is torsion free. Okay, so when applied to some function f, this term here is 0. And we have only this term here. This other term here, we can write it as at least multiplying and dividing by f, capital F. So and now this is important because we want to write again this n mu. How? Well, if we, for example, here write something like this, we just multiply and divide by f, we figure out that the gradient, the nabla applied to f, only capital F, divided by f, is just the gradient of the logarithm of f. And what is remaining is the capital F, which multiplies the other gradient applied to small f. And that's the n mu itself. So here it will be just this, as you understood, I guess so. And yeah, this number is applied only on this, okay? And the remaining is n sigma here, the antisymmetrization. And so now we know that this q sigma nu contracted with n sigma is 0, because we said that this n is orthonormal and this q is just the metric tensor on this sigma here that is spatial. Okay, so that's why this is all vanishing, and so the antisymmetric part is 0 and it's only symmetric. Okay, so now quite far here. I cannot see the rubber on the screen. Okay. Okay, sorry. Okay, so now let's go on. And if you remind, the last action that I wrote was the very long action written in terms of the metric tensor and some other quantities. But let's go back just for a while and say that the action that we wrote just a step back is this. Where I remind you that this K here is just KAB, QAB. Oops. Okay, QAB here. Now, we also used such a formula. Because now what we want to write is the action instead of in terms of the extrinsic curvature, or at least better saying the pullback of the extrinsic curvature down to the sigma, to write it all in terms of the metric tensor, the derivative of the metric tensor, the Lopes function here, and also we have the shift vector in here. Okay. And another thing is I want to remind you that the derivative can be written in this term here. And again, I remind you how we constructed this covariant derivative capital D from the nabla one we had in 4 dimensions. You know, just say that this is compatible, spatial, and torsion free again. So okay, I guess this is quite simple. The derivative written in this term here, and now using these formulas here, we can write the action here as the long action that we wrote, but I'm not going to write it all because it is just a loss of time. So just the beginning, just to say what we want to do. All right, this is the R3 is the Ricci curvature on sigma, sorry, Ricci scalar. 1/4n, and we have all the terms here, AB, Q prime AB, minus 2, all this term here, and this of course involves the shift vector, Q prime AB plus, and so on and so on, okay? So now it's not important what is written in here. What I want to say, that's the only thing that matters here, is that we can write the action that depends only on QAB, Q prime AB, and A and N. So we have the derivative of QAB in here, but we don't have the derivative of the shift vector and the Lopes function. This is very important because this tells us that the shift vector and the Lopes function are not dynamical variables. So now, oops, no, maybe. I don't know how to switch. No, I'm sorry about that. It's the first time that I'm using this. Usually I used to use another.
What do you want to do?
To use another
page?
Yes, exactly.
Yeah, I can Google it quickly and then tell you.
No, sorry about that, because I used another one that is not working, and now I'm going to use this for the first time. Yeah, I don't think there is some. Okay, I have to erase everything here, but okay, no, it's not important. It's not important now.
Yeah, they say on Google that you cannot add a new page.
Okay, thank you, Microsoft. Okay, the only thing now is matter that we got that this S depends on QAB, as I wrote, Q prime AB and A and nothing else. Okay, so now we want to find out what are the momenta associated to these variables here. And again, as we do in the classical mechanics, analytical mechanics, this P is by definition, the momentum associated to the metric tensor. So it will be given by this, as you know, And this is just the square root of q and qab minus qabk. Okay. And now what are the momenta associated to the shift and lapse? Of course, they are vanishing because there is no...
What is square root of q? Is it trace or determinant?
No, the square root of the determinant of q. Yes. Yes. Because I'm going to write the determinant of q as just q, just written in this way. So these are the other momentum, and prime a at x equals 0, and also pi x is 0. Sorry, n prime is 0. Now, first of all, these two, which are 0 in this way, are called primary constraints. Okay, these primary constraints, at least are the conjugate, the momentum associated to some variables, some coordinate variables, which vanish. Okay, and now the procedure created by Dirac is that for any primary constraints, vanishing primary constraints, we have to add to the Lagrangian multipliers associated to such primary constraints. So we have to add Lagrange multipliers lambda a lambda, in this way lambda a pi a plus lambda pi to the Lagrangian. Okay, and now I have to delete everything again, but we are not going to use all of this, so it's just a concept. Now we can rewrite again the action in such a way that we perform a Legendre transformation, and we would like to recognize the Hamiltonian coming from this, because we know that the action can be written, is just integral over time of the Lagrangian, and that the Hamiltonian comes from the sum, or say the integral in terms of the if we are on a manifold of the terms like the derivative of the coordinate multiplied by the momentum minus the Lagrangian. Okay, so we would like to write this in a different form, so that what we do here, here QAB here, PAB plus n prime a pi a plus n pi, and this is the procedure, plus minus q prime ab PAB plus, as we said, adding this term here, the Lagrangian multipliers, minus the Lagrangian density here. And of course, this is not clear from here, but what will happen is that this lambda a will be equal to n prime a, and the lambda will be equal to n, so that in total all these terms cancel out. But what we do here is that we can, of course, we cannot solve all the velocities for the momenta, or the other way around, because we have some primary constraints. So we can just solve some of them for example, the Q prime AB and PAB, but we cannot solve the pi A with lambda prime A and also pi with N. So that's why we want to only use some formula to rewrite this in another way. And I give you the formula. Oops. It's just a matter of calculation, so it's not so important. Again, we have this square root of Q, QAB minus K squared. Okay, so we use this formula and rewrite it here. And also, you remember that this ln Q, and I'm going to rewrite it.
So where did you get this formula from?
Well, you get it from the PAB. I wrote it. That was. I wrote it just above. So I want to maybe write it here. PAB was the square root of Q KAB minus QABK. Okay, and this Q prime comes from the QAB formula. That is, again, I'm going to write this. Just want to find it. Okay, maybe I remember. We have QAB equals 1 over 2n Q prime AB minus this. Okay, so we just from this we have the QAB equals 2n KAB plus the derivative. Okay, and if we multiply by PAB, which is given by this, then we have all of this. Is it enough?
In some places you replace PAB, and in other places you don't replace PAB.
Yes, exactly. I don't want to replace because if we get, if we want to leave all of this here and have something else in here, what we get is that this term here will be the Hamiltonian.
What is the definition?
Well, just because we, from the Hamiltonian, we have that it's just given by Q prime AB PAB plus these two terms here, okay, which are equal to this minus the Lagrangian. No, so just the Lagrangian transformation.
Yeah, I mean, it's just the definition of the Hamiltonian.
Yes, exactly.
But he's replacing the velocities with momenta, so the Hamiltonian should depend on the momentum.
Right, but
that's all that's going on.
PAB is the momenta associated to Q, but you can express it completely in terms of Q and the
yes,
external derivative, exterior derivative.
Yes.
So it's not clear.
Well, here, what we are doing here is that we solve this because we can solve this because it's not a primary constraint. We derive that PAB is given by this term here.
Yeah, no, but that's what is strange. Why is PAB given in terms of that? PAB is the momentum. It's not, you cannot if the
well, no. Well, of course, this PAB. If you want to, this KAB is given by also the derivative of the metric, and so when we replace this KB here, we get that.
okay, so but then it's wrong to have KAB in your action, or in your Hamiltonian. Sorry.
Yeah, I mean, you can also rewrite. Yeah, as you say.
You should write it. Take away all the KAB stuff and just write everything in terms of PA.
Yes, exactly. Yeah, we can do that.
Yeah, you should do that.
Yeah, of course. No, I just want to show that this procedure here is what we. I mean, I was trying to say that we want to replace this QAB PAB in terms of this, and also I'm going to write some other formulas of K, this term here and this term here, just in terms of P. Okay. So the other formulas are that PAB equals the determinant, not the square root of the determinant, KAB plus K squared, and also another one, P squared given by 4QK squared. And again, P squared is given just PAB, QAB, just the the contraction between P and Q. So in terms of this, we can rearrange this, all of this term here, and write in just in terms of PAB, and P squared. Okay. So yes, the next step is, I just gave you the formulas and what we need to do that, and so I'm going to write only the result, and so we have that the action here will be this integral of t, this 3x of q prime AB PAB plus m prime A pi A plus n pi minus lambda A pi A plus lambda pi, the same thing, I don't want to do that, plus NA HA plus NH, where HA equals minus 2QAB, sorry, AC dB.
Why do you have an NA dot but not an M dot in the first line?
Oh, sorry. Thank you. And H given by this. This is just, I know that it's a long way, but I mean, it's not long, but I'm trying to avoid all this calculation, just substitute quantities in terms of the momentum and try to rearrange and perform when it's possible some integration by part and cancel the boundary terms. Okay.
And there is no square root of Q outside the whole parenthesis in the measure?
Yes, thanks. I forget something here in the way.
Sorry, Giacomo, is there no square root of Q in the measure?
Here.
I don't know where here is.
You can you mean here, like square root of Q?
Yeah.
No, of course not.
Why,
No.
of course?
Well, the square root of Q will be only in here and in here.
Yeah, but why, of course? Why shouldn't there be I mean, the measure then is not, a, 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 a,
But you have to, you know, I mean, this PAB contains the square root of Q. Exactly. Yeah, you remember that PAB is square root of Q and blah 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 something else. Of course, this is 0, this is 0, and also this will be 0, so it's not important here. And here you have again the square root of Q here, and here we have the square root of Q. So actually it's hidden, but there is.
So that, I mean, it means that on sigma, if your measure is not a tensor, then neither are your objects. So H doesn't transform as a tensor, but as a density.
No. But I'm sad that PBC contains the square root of the metric.
So it means that it's not a tensor.
Well, if you define the Lagrangian to be a density of the variation, which gives you P, so
yes, exactly. Yeah, it's of weight 1. It's a density tensor of weight 1.
So you're saying the momenta are not if you define it including the square root, then they are not tensors, and that's why
it's a density tensor.
Yeah. Okay.
Instead, Q of course is a tensor, but the moment is as I told you, a density tensor of weight 1, because there is directly the square root of Q, and that's it. Oops. And here we have PAB minus 1/2 P squared. And again, you see again that you have the square root of Q here, the square root of Q here. So in total, H again has a square root of Q. And again, it's a density scalar here. Yes. Okay, this comes just from, as I told you, some substitution and integration by parts. So this is say almost the final result. And so what we get here is exactly the Hamiltonian here. So we can write all the Hamiltonian. This is, I'm going to say that this is called the diffeomorphism constraint, and this is called the Hamiltonian constraints, or also the vector constraint and the scalar constraint. This is, okay, maybe the notation is quite misleading, but it's important to, at least to me, to write it as H, because they are, say, as I told you, the Hamiltonians. So the total Hamiltonian here will be just the integration over the 3x of the lambda a pi a plus lambda pi plus NaHA plus NH. Okay. All right. Now, there are very questions to address. The first is the consistency of the constraints, and I'm going to tell you what it means, and then to compute the Poisson brackets, because we have, of course, all the mathematical tools to do that, because we have a volume form, we have that, I mean, it's possible to construct Poisson brackets. We have all we need. And so the Poisson brackets here are between the momenta, say at a fixed t, so only on a single space like surface, not compared to the others, because we are working only on one single sheet. At different points, sorry, and this is the symmetrization of this CD, which corresponds to the symmetrization of also AB, and of course the Dirac delta at different points. Then we have also the other conjugate variables. And the last one, which is pi and n. This is just delta x minus y. And all the others Poisson brackets are vanishing. So using this, we can compute also other Poisson brackets between the Hamiltonian and variables that I'm going to do right now, because this is important. That is, if we want to calculate, for example, the derivative of the momentum associated to the shift vector, by consistency, this has to be zero. I mean, not equally zero, but at least weakly zero. That is, just on shell has to be zero, because this is not a dynamical variable in the system. And this is, by Hamiltonian mechanics, that just the Poisson bracket between Hamiltonian and pi a itself. And we can compute it because now, working in a manifold, we have the integral over d3z, of course, on sigma of the variation of the Hamiltonian. Yes, first the Hamiltonian, then the densitized delta pi bz and delta pi a x delta n bz minus the opposite okay. Of course, this is zero because the variation of pi with respect to n is zero. But of course, we have that this term here is just the delta, the Kronecker delta, and the Dirac delta. And the Hamiltonian here, when we write down the Hamiltonian in terms of the what you wrote, it is the sum over all those other terms. This is just minus the integral of d3z of delta AB delta 3x minus z coming from this one. And the variation of the Hamiltonian with respect to NB just gives the said that the Hamiltonian is given by this. HA plus NH here, and we have the variation of all of this. Oops. Of course, this is with y, okay? So the only term here that matters is this one. All the other vanish. So what remains here is just the integral over d3y of the Dirac delta and HA. So or maybe it's better to write it as NCHC. That's better. CB y minus z again, and HCY. And now when we contract, of course, this and this just gives, or maybe, what was that? Oh, sorry, it has to be, no, sorry, it has to be, it has to be B here and A here. Yes, because of, this has to be here, yes. So, yes, okay, so we contract this and gives just the delta CA again, which when applied again to HC gives just HA. And all the delta, I mean, when we integrate out this over d3y of this delta here, and this delta here just gives the integral in d3, the Dirac delta of x minus z. And so at the end of the day, it just gives minus h. Can you see that?
Yeah.
Okay. So minus HA at the point x. And this, as we said, by consistency, has to be equally zero. Sorry, weakly zero. So only on shallow. So that's why this is another constraint coming out from this consistency of the evolution of the momentum, which were not dynamical variable. And so this is again a constraint, this HA, and it's called secondary constraint. And such a secondary constraint also, as I told you before, this one HA is called the diffeomorphism constraint. Okay, so we got a secondary constraint, and we go on to find what are the other secondary constraints. And of course, the other condition that we have to impose is that not only the consistency on pi A has to be applied, but also the consistency on pi itself. So the momentum conjugated to the lapse function n. And if we do the same thing here, we have that pi prime at x, again given by h pi, it's just given by minus h of x. And again, weakly zero. This is another secondary constraint called also the scalar constraint or the Hamiltonian constraint. And so from this we have as secondary constraints pi, HA at x, that I write again because maybe it's important. Minus QAC dB PBC equals 0, and HX weakly 0 again. And this is called the secondary constraint. Now, if we want to follow again this method here, we would like to know if there are tertiary constraints. But this is not the case. When we try to evolve these new constraints with respect to time, they are equally zero. That they're not given by some formulas, it has to be weakly zero, but they are identically zero. So there is no further tertiary constraints. And so the procedure stops. Now, another thing is that we want to also to compute the evolution with respect of the lapse function and the shift vector. In this case, the shift vector, so not just at x, given by, again, h and a at x. What it gives us is that when we again use the total Hamiltonian greater in terms of those sums that I wrote beforehand, this coincides with lambda a, the Lagrange multiplier. So we can say that such a Lagrange multipliers equals the evolution, say, time derivative of the shift vector. That's why at the end of the day, in the action that I wrote above, we had plus minus terms involving n prime a and lambda a, because at the end of the day, they cancel out. And the same for n, and of course, as can you guess, this is just lambda at x. Okay, so for now, this is at least something we can say so many things about all this method here. Of course, that's very known to everyone, but this is at least the least, okay, to understand what is going on. And now we would like to know what is the algebra of such constraints, what they mean, and what is not also the geometrical meaning that they give to the framework, but also what they mean when we want to quantize the system. Okay, because we have to take into account also gauge transformations, and so all the symmetries of the system, and also the constraints that play a crucial role in it. So now it's almost 2, but tell me if you want to continue or want to stop here and continue next time. Let me know that.
So how long would you continue for? Do you want another hour or 15 minutes or what?
Well, the algebra actually takes I think half an hour.
Yeah.
Because if I start doing that, then I think it's a good thing to continue till the end of the study of the algebra. Otherwise, I think it's a nonsense just to stop it in the middle.
Yeah.
So let me know.
Yeah, I think half an hour is okay for me. So I don't know. What about the others? I think if you were to continue for like an hour, that might be a bit too much, but I think half an hour sounds okay.
Yeah, of course, depends also on some questions or something that might prolong it.
Yeah, of course. So are people okay with continuing? Seems so. So yeah, please.
Okay. Okay, so Now, I want to write again this HA and H because we want to study them. So -2 AC. Okay, now of course this is all at x and at x. Now, you know, we calculated the Poisson brackets between the conjugate variables. We can also, and we would like to compute also the Poisson brackets between HA and itself, between, I mean, all the combination between HA and H and possibly also with all the variables of the phase space. And all of them are distribution. We saw that all the Poisson bracket get Dirac deltas. So this, of course, is not something very nice when we want to study the algebra, because first of all, we don't have, we don't want to have such say ill-defined quantities. We would like to have some smooth results, so something that has been smeared. So one thing to do is that, well, I can take this HA and to smear also H and to smear them out with some other functions, test functions. So if you want to write this H and written in this way, just the integral over the x of n a x h a x. It is over sigma, of course. Because in this way we have an integral which cures all the Dirac deltas, and the same for h without of course the arrows. Of this n a and n are arbitrary functions, test functions, and they are exactly, well, we can construct with this so that you remember in the total Hamiltonian we had this term here and also this term here in the sums with the integral. So actually the total Hamiltonian H can be written just as, you know, lambda pi, the same way, the same convention or notation. Sorry, pi here plus H n plus H n. Okay, so that's another way to write it. And so yeah, we want to compute, so the Poisson bracket, instead of between HA evaluated at a point x of the manifold, the smeared ones. Okay. So for this, it's quite long to do that, but I mean, at least it's quite important. And sorry, before I want to write this, Oops. What changes is that instead of performing this Poisson bracket between the constraints at different space-like points, we want to evaluate it at different test functions. That will be the difference between these two approaches. Okay, and so this, just the 3z of delta H, and we have delta P, A, B, Z, delta H, M, delta Q, A, B, Z, and minus oops. And now when we substitute this, the formula for this the smeared ones, which is given by N, A, H, A, and HA, we know in terms of the metric tensor and in terms of the PAB. Okay, and then we will get just the Dirac delta that will be neglected, say, by the integration, actually integrated out by this integration. So what we'll get here is just the integral of d3z of PAB x z of the derivative of the commutator between M and N, okay, and Q A B evaluated at Z. Okay, so such a Poisson bracket gives this, and you can ask, what is this? Well, it comes from the fact that, written in other terms, this H and is given by this. Okay, that's another way to write by integration by parts this smeared vector constraint. And so what this Poisson bracket does between one and the other is just to shift the to shift itself. This vector constraint here has the purpose to shift itself, because we know that the Lie derivative of the commutator here is just the commutator of two vector fields. Just by the property of the Lie derivative, it's just the derivative of one onto the other. Okay, so it will be just dragging again the Lie derivative. And this is why such a constraint is called the vector or the diffeomorphism constraint, because it shifts any quantity along the test function, which in our case is the lapse, the shift vector. And so more or less this is the meaning of such Poisson vector constraints. And if we want to apply, if you want to compute also the Poisson bracket between any function of the phase space and such a smeared constraint, this smeared constraint has the purpose to shift also the function. So it will give us the Lie derivative of the function. Okay, so also we want to write also the Poisson bracket between the vector constraint and the scalar constraint, and also the Poisson bracket between the two scalar constraints. Okay, so I just give you the result because it's important to understand the geometry and the meaning of those instead of all the formulas and calculations. So written also in other terms will be just yes, instead of with the derivative, with the Lie derivative, we have the commutator of these two, which correspond to the Lie derivative of n on m. Okay, and also now we have between h n and h m, which is given by h of the derivative of m on n. Okay, so again, this vector one, what it does is to shift by Lie, so dragging such a function along the m vector field. And lastly, we have this one, which is a little more complicated, and with the minus here, s okay, now this s is a function of the two test functions and m, and also the metric q. And explicitly, this in components and coordinates is given by this formula here. Now, the meaning of this is a little more tricky and complicated because you don't understand what's going on here. Roughly speaking, this H does the following. It drags. So maybe it's better to have this written in this way. We have a point x here, and remember that we had, in the construction of the deformation vector and the splitting of the spacetime to 3+1, that these 2 point x are, say, space-like equivalent. So this is called the the what I call the T mu vector, and this was the normal vector and mu, and this is the n mu here, the shift vector. So this T mu is given by a combination of the shift vector and also the Laplace function which multiplies the normal vector at a point x. So this T mu is quite tricky because actually it cannot be seen, but it's it gives exactly the deformation of the two sheets that correspond to equal space points. And this H now has the meaning to shift, say, a function or any other quantity defined with variables on the phase space along this T mu vector. So it drags it over time. And that's why it's called also called the Hamiltonian constraint, because we know that Hamiltonian gives the time evolution of the system. And so more or less, say, even though we don't have a very proper physical time in here, just a parameter t which describes two or more different sheets of defoliation. Actually, the drag along this T mu between two time separated surfaces but space equivalent actually gives this Hamiltonian constraint. So it has the if we have this vector constraint or diffeomorphism constraint has the meaning to drag quantities in here in this sheet. Instead, this H has the meaning to shift along another one, actually, or maybe better saying along the evolution, parameter evolution of the sheets. And of course, this here is not very very clear. Or sorry, B here. It's not very clear from this, but actually that's the meaning.
Can I ask?
Yes.
So in the third bracket on the right hand side, shouldn't you have arrows on both H and S because they're vectors?
Sorry, can you repeat again?
In the third bracket on the right hand side, you have H and then S inside the bracket. Shouldn't both have arrows? Because so you defined S with an index, so it's a vector. And you did not define what is a scalar in your notation. You did not define what
yes.
H was a scalar.
You mean this?
Define. Yeah, and then if you write it like that, then you would also have to have an arrow on H because you did not define what would be a smearing of a scalar with a vector, right?
No, I'm not following you actually.
So, okay, so you defined S with an index. So that means S is a vector, right?
Yes.
And then you introduce this notation of this smearing out by writing a function or a vector and then something inside the bracket.
Yes.
But you did not define what would be a smearing of a scalar and then a vector in a bracket, which is what you have written on. Or at least I don't remember.
No, I did. No. I mean, you're right. There has to be H. Yes.
Okay. Yeah,
yes.
then that makes sense to me. Okay.
Yes.
Yeah, thanks.
Okay, so let me clear this. Erase all of this. Okay, and now what I wanted to do is also, I mean, all of this 3 plus some brackets give you the algebra of such constraints. In the next talk, I will rewrite all of these constraints in terms of other variables, as usual variables in terms of connections. And so there are some other constraints with that emerge from that. For example, the Gauss constraint, and the meaning of those will be more clear than, I mean, much clearer than the one that I wrote here. Yeah, of course, I don't have the time to speak about the tetrads and triads in order to introduce those connections and gauges. So yeah, I guess it's more or less all. Maybe what I can do a little bit more is just to, if you want, I can show you why the shift vector, for example, shift any function by Lie, if you want.
Didn't you show that already, the calculation?
No, well, just on the constant itself, but not on any function of the phase space variables. Or at least how it works. I mean, how the Lie derivative emerges from the variation of the of a function of the phase space variables, and from that, how the vector constraint affects the Lie derivative. And so at the end of the day, we have that the Poisson bracket between the vector constraint and any function gives just the variation, the functional variation of the function itself, which corresponds to the Lie derivative of the function along a vector. But if you, I mean, already know this, because it's not something about general relativity or this scheme, this formulation is more general. So if you want, I can show that briefly. Otherwise, that will be all.
Okay, so I mean, if you can do it in a reasonable time, like 10 minutes, then please feel free to do what you said. Or if it takes a longer time, then I would suggest that you can postpone it to next time.
Yeah, maybe 10 minutes. Well, maybe. Now, maybe I guess it's better to do it next time with again 1 hour and a half, and
I think that's reasonable time.
yeah, and the next time hopefully it will be in person. I don't know, because in middle May I'll come back.
Okay.
And so it's more or less half of a month from now on.
Yeah, so 2 weeks, right?
Yeah, 2 weeks. Yeah, 2 weeks. 2 weeks, or yes.
So we have it on Thursday, so it will be 12th of May. Would be in 2 weeks. So I don't know if you will be already here.
Yeah,
or
next. It's the 12th of April. It's a bit borderline. I don't know. I have to say.
Yeah, well, like,
Okay,
we can discuss after this, or if anyone else wants to give a talk in the meantime, because other than you, we have only Dirac, who was doing the geometric algebra. So I don't know if people are interested in continuing that. Yeah, I'll just have to like ask everyone, and then you can continue in person if you want, or again online. But if we have anyone else, that would also work. So just let me know, and yeah. Okay, so thank you, Giacomo, for the